Hello everyone and welcome to Noer Yudarris. This is your host Mahmoud Noer. Today we'll be talking just quickly about bonding and organic chemistry and quantum numbers and the placement of electrons. So it's going to be a quick video and stay tuned please. Don't forget to like, share, subscribe and leave any comments for any topics you want me to cover. So basically we're going to be speaking about quantum numbers. Quantum numbers are the numbers that help us determine where to place the electrons when we're given an atom, where to place them on like shells and subshells. So N, we're going to start with N. It's N, L, ML, and MS. N is the measure of the size, size of the what do you call it, the shell. So the smaller the number, the lower the energy. So let's say you have what, four, like n is equal to 4. It means you have four shells. All right, you have 4 levels. All right, and then L is the subshells. L is the subshells. So how many subshells you have? You have like a S, you have a P, you have a D, you have an F. So they're numbered from 0 to until now we're just gonna stick to 3. We're gonna just cover the 0 to 3, and then you have the ML, and these are the position of the electron on the subshell. Ranges from -3 to 3. So -3, -2, -1, and then 0, 1, 2, 3. And then lastly you have the MS, which is spin, and the basically it's paramagnetic or diamagnetic. That's what MS is essentially here for. And quantum numbers, like I said, describe the size, shape, and the number. So for instance, you have the S subshell, and S subshell is always a 0, and ML is 0. Its orbital is 0 because there's only one subshell, so there's only one place to place 2 electrons, maximum of 2 electrons. And then you have the P subshell, and the P subshell is numbered as the L is equal to 1, and then the ML is -1, 0, and 1 because there are 3 spots where you can place a total of 6 electrons. Next you have D. D is numbered as L is equal to 2. So it's ranging from ML is ranging from -2 to 2. There are 5 spots where you can place 10 electrons, because remember, each spot you can have a maximum of 2 electrons. And then lastly, F is L is equal to 3, and then ML is from -3 to 3. So okay, let me give you an example. For instance, you got I want to say hydrogen. Okay, how many electrons hydrogen has? All right, hydrogen has a 2 electrons, so it's gonna have an s orbital. So hydrogen, for instance, is gonna be 1 H2, and then it's gonna be s because it has the s orbital, and then its ml is 0 as well, but it's gonna have a maximum of 2 electrons out here. That's bad handwriting, but nevertheless. Next you have the molecular orbital. It's when 2 atomic orbitals combine. So basically this is the structure for it. So let's take hydrogen again. You have 2 parts. Let's say you're bringing a hydrogen and a hydrogen, and then you have 2 parts. You have the antibonding and the bonding. With the bonding, it measures really a how good the stability or how good it is to find the electron in a specific region. With the bonding molecular orbitals, they are low in energy and they are stable than the anti-bonding, because you see, as you go from here from a higher to a lower, you're releasing energy, and it's easier than you putting energy and going to a higher energy level. That's why they're less they're lower energy and they're more stable. They release excess energy. So we got a couple types of bonding molecular orbitals. You got the plus and plus, for instance, here and here, which will give you one big area, and then you got the antibonding. The antibonding is basically a high energy and it's less stable. You need to put in energy to get to the higher energy. Usually the systems prefer to go to a lower energy than a higher energy. So for instance, you got plus and negative, you're gonna have a node in between, and that's not what we prefer. Next, you're gonna have a bonding molecular orbital, and again, this could be one of the types as well, where it's like two positives, and then there could be a negative in there as well. And then you got one last one, a negative and positive and negative. They're close to each other. They're not really away from each other. They combine to form a bigger one, and then they have the negatives on the side. Next, we have the bond order. Bond order really helps us describe whether the bonds are stable or not. I want you to remember far back to sigma and pi. Remember, I mean the S and the P characters. Remember when we said the sp3 is one of the most stable ones, or the strongest one, my bad, the strongest one, versus the SP, which was a single bond. Here, bond order, the higher it is, the more stable it is. So bond order 3 is the most stable, and it's a triple bond, and it's the least reactive because it's the most stable. Next, you have the bond order equal 2. It's basically a double bond. And then you have the least stable, a single bond, and it's the most reactive and the easier to break. So an anti-bonding could be a less stable, could be a single bond, versus a bond order, a bonding molecular orbital with a triple bond. And then what if you get in the question, for instance, a bond order equals 0, means there is no bond formed, such as a gas, for instance. In order to calculate the bond orders, so it's basically the bonding electrons minus the anti-bonding electrons divided 2. Let's say you have H2 here, and then you have 2 minus 1 divided 2. That's what do you call it? A negative. That's by the way a H2 with a negative up there, and then you're getting half. That's an instance. Or for instance, let's say, I don't know, you're getting an example of like helium. Okay, what if you get helium? Okay, if you get helium, alright, what are you gonna do? So it's 2 and 2, because helium has 4 electrons. 2 are gonna go in the bonding, and then 2 are gonna go in the anti-bonding, because you need to fill the bonding first before you fill the anti-bonding. And then it's gonna equal to 0. It means there is no bond, essentially. With an example like a helium, I want to point out that helium has 2 ends, has 2, the size of it is 2, because it has 4 electrons. So once it fills the 1s, it needs to move up to 2s. So that's the antibonding area, versus this is the bonding area. Alright, let me just bonding, anti-bonding. Alright, well, that was a quick video. Thank you so much for tuning in, and hope you have a good rest of your day.